Okay, so today's 10.3, simplifying radical expressions. All right, so all the things that we learned with our radicals, all the tools that we have involving radicals, we're not going to use them to actually solve. To actually, sorry, my cat. We've got two windows, and he wants to poke his head through the one that has blinds down. Like the other one's right next to it. What's wrong with that window? So anyway, sorry. Now we're going to use everything we learned to actually do the arithmetic involving radicals. Okay. So first things first, we're going to be the again. Okay. Well, never mind then. Okay, if I can put this over here, and don't know if this will fit. Probably shouldn't even try, huh? But we're going to. Oh, it does. Look at there. Look at there. Okay, so simplifying radical expressions, we're going to start over here to the left. You may have already noticed certain properties of radicals involving a product or quotient. Multiplication property of radicals. All right. If you do need to message me, again, message sample student, or just message in the group chat. Okay. Anyways, so again, multiplication property of radicals, we're going to let a and b represent real numbers such that the nth root of a and the nth root of b are both real numbers. Again, meaning that we're not going to have imaginary numbers. Okay. Then the nth root of a times b is the same thing as saying the nth root of a, times the nth root of b. Okay. The multiplication property of radicals follows from the property of rational exponents. The nth root of a times b is what we did last Wednesday. The a times b raised to 1 over n power, and then when we do that, we know that we can separate them apart from and have the nth root of a over the nth root of b. Okay. The multiplication property of radicals indicates that a property within a radicand, again the radicand being what's inside, can be written as a product of radicals provided the roots are real numbers. Again, they have to be real numbers. Okay. So for instance, the square root of 144, okay, can be broken down into a square root of 3. I'm sorry, a square root of 16 times the square root of 9. The reverse process is also true. A product of radicals can be written as a single radical provided the roots are real numbers. So we can go the other way this time, right? We can multiply the two numbers that, well, the arrow went a little far. We can multiply the two numbers that are inside the radical, right? 3 times 12 is 36, so we can do this, right? So we can go in both directions with our multiplication property of radicals. Okay, so simplifying radicals by using multiplication property. Okay, this is all right. So in algebra, it is customary to simplify radical expressions. So simplified form of radical. Consider any radical expression where the radicand is written as a product of prime factors. So, well, these aren't written as a product of prime factors, so that's not a good example. Maybe we'll get to an example here in a moment. The expression is in simplified form if all the following conditions are met. Okay, the radicand has no factors raised to a power greater than or equal to the index. Okay, so let's actually just do this. Oh, here we go. They're down here. Let's see. Okay, so this is condition 1. Okay, so it says the radicand, again the number inside the radical, has no factor raised to a power greater than or equal to the index. So here's 1. We have the cube root of x to the 5th. Maybe again when we get to radicals, it gets a little hard to see things. Maybe this will help. I don't know. We see that this is a cube root, and there's an x to the 5th. So this says that this expression fails condition 1, which it does, right? Because condition 1 said the radicand, again the number inside, has no factors raised to a power greater than or equal to the index. Well, this is raised to the fifth, and the index is raised to the third, so it fails that. Okay. So number 2, the radicand does not contain a fraction. So we see that, well, I mean, that's pretty easy to tell, right? We have a fraction. And 3, the expression, 3, there are no radicals in the denominator of a fraction. The expression 1 over the cube root of 8 fails the condition. Okay, that's pretty easy, right? I think number 1 might be the one that is kind of the hardest maybe to wrap your head around as of right now, but we'll definitely get to an example here in a moment. Okay. Matter of fact, let's just get to the examples. It's a lot of words to say nothing, huh? No, there's a lot being said. Alright, so this reads, simplify the expression assuming that x is greater than or equal to 0, and we have the the square root of x to the 9th power. Okay, so x to the 9th power, let's write it, let's put the little 2 there for right now, just to really drive this point home. X to the 9th power. Okay, we know that 2, when we have a square root, we know that the 2 is implied. We don't have to put the square there. But for now, we're going to, okay? So we can go about writing this a couple of different ways. One of them, we're not going to write this way, rather, but we're going to view it in this lens here. Right? That's what we did Wednesday. We know that the square root of x to the 9th is the same thing as saying x to the 9 over 2 power, right? Okay. Well, we can think of this as, okay, well, 9 over 2, well, what is 9 over 2? Well, you know, that's 8 and a half, or I'm sorry, 4 and 1/2, right? So we can think of this kind of like that, right? All right, first of all, let's erase this one because it kind of looks like a squiggle, right? We don't want squiggles there. Okay, so that's essentially the path we're going into. Is we're going to be taking this rational exponent and reducing out the whole numbers. Okay, so again, let's put it down here now, and we'll go and x to the 9th. Okay, so we can essentially think of this as x to the 8th times x. Okay, so why can we think of this as x to the 8th times x? Well, if you recall from your exponent rules here that we went over, if you're multiplying exponents with like bases, then you add those the exponents there, right? 8 plus 1 is 9, so that's where we have x to the 9th, and it's equal to x to the 8th times x. Okay, and then following along into the same pattern that we did earlier, we're going to put this into the square root of x to the 8th times the square root of x. Okay, oh man, another morning I'm struggling, huh? Man, it's these early classes. I'm just not an early class person. So anyways, now we can say that the square root of x to the 9th is equivalent to the square root of x to the 8th times the square root of x. Okay, using again what we did last Wednesday and what we saw on the previous page. All right, and then from here, well, we know what the square root of x to the 8th is, right? Because again, let's go ahead and take this and write it with the rational exponent. This turns into x to the 8 halves, right? Because again, it's a 2, and then times. We'll just keep the square root of x as the square root of x. Okay. Well, what is x to the 8 halves? That's x to the 4th times the square root of x. Okay. And that's our solution. Now, the reason why I wanted to go about this route first is because I feel like it really, realistically, all this, we didn't have to write all that, okay? If we can just think of, or if we can remember what we did last Wednesday, and we can kind of rewrite things in our head. And again, the first example is easy, and they all are pretty simple because we're only dividing by 2, 3, or 4 realistically, right? Or we will be rather. And so you just say, okay, so how many whole numbers, how many times will 2 go into 4? Okay, well, I mean, so how many times will 2 go into 9? Well, 2 will go into 9 4 times. Okay, and then how many will be remaining? Well, that would just be 1. Okay, so I'll try to do another one with that thought process real quick, and then I'll also do it probably the way the book, the textbook wants us to do it this way. And maybe I over-explained because that's not a lot written compared to what I did. Okay, so we'll do A. Let's make these a little bigger. Okay, so A is, so we would ask ourselves, okay, so looking at the problem, and let's go ahead and rewrite it so I can actually, point arrows and stuff around. I don't like the way that 7 looks. I don't like the way that 7 looks. I don't like the way that 7 looks. That 7's gonna have to roll, okay? Alright, so we would ask ourselves, okay, so how many times will 4 go into 7? Well, it'll go into 7 one time, okay? Alright, so what we're gonna do is we'll say that it goes into it one time, so we're gonna have a b out on the other side of the radical, okay? Well, how many b's would be left over? Well, that would be 3 b's, right? So it'd be b cubed. Okay, now let's do it the way the textbook probably wants us to do it. So we're going to go, we'll put this in yellow. Okay, so what we'll do is we'll say the fourth root of, and we'll break it down into b to the fourth times b cubed okay. Well, there we go, close enough. And then of course we know that we can make the fourth root of b to the fourth times the fourth root of b cubed. And then what is the fourth root of b to the fourth? That's b, and then the fourth root of b cubed. They all look like y's. I'm really sorry. Again, it's just I can't write small on these on this particular program. It looks like, but at least I'm saying it out loud, right? So again, either of these methods, and I do feel like the top method is the one you'll probably just kind of fall into once you get a full, a nice understanding and you're really comfortable with your radicals. At least it seems that way for many students. Okay, so B. Okay, so B is the cubed root of w to the 7th times z to the 9th. Okay, so I'm going to take this again. I'm going to take this just slowly. I'm going to say the cube root of, and what I'm going to do is I'm going to say w to the 6th, w to the 6th times w. Okay, again because I am asking myself, okay, so what is the largest number? What is the largest multiple of 3 that would go into 7? And of course that would be 6. Okay, and then I would say, okay, well, what is the largest multiple of 9? I'm sorry, what is the largest multiple of 3 that will go into 9? Okay, well, obviously that's pretty easy, right? 3 will actually go into 9, so that's good. Right? And something that I would do if I did it this way, or what I always did rather, is I would take this and I would underline what I'm taking out. Okay, it makes it a lot easier for me. It did make it a lot easier for me, right? So now I'd say, okay, so what is the cube root of w to the 6th power? Well, that is w squared. All right, and then what is the cube root of z to the 9th power? Well, that is z cubed. And what remains? Well, that would be the cube root of w. Okay, so real good. I mean, I kind of showed you 3 ways how to go about this in these 2 problems, right? This one, probably my favorite because it's just quicker. But if you're just starting out, this way would be the slow but sure way. And another way, of course, this would also be a slow and sure way. Okay. And honestly, I'll probably do it the rest of the lecture the way I do B, the way I did B today. All right. The following lectures I'll probably just go quickly like I did in A, but the remainder of today I'll do it the way I did it in B. Or yeah, B. Alrighty, so in the past I have said you need to memorize your squares up to 10, maybe 12, right? And your cubes up to probably like 5, right? And the reason for that is because you need to be able to identify uh, perfect square factors. Okay, what is a perfect square factor? Well, let's imagine. Let's see. We'll do 32. Well, I mean, we actually have a problem, I know, but let's just look at 32 real quick. Okay, so I know that 32 has a perfect square factor, right? Because if we did our factorization tree, I've got 16 times 2. Well, 16 is a perfect square. Okay, I need to be able to recognize that a perfect square is a factor of our number. Okay, the reason why is because we're gonna be taking that perfect square and essentially taking it out of the square root. Okay, and again, we're gonna see that here in a moment. So let's do this. So we've got the square root of 56. So let's just write the square root of 56 right here. Okay. So on these problems, you need to again recognize if you have a perfect square factor, and the way to go about this, I won't say pretty simple, but you can say, okay, so 2 will go into 56, and it would be 2 times 28. Okay. In that form, we don't see a perfect square factor. Okay, in that form. All right. So next we'll go to 4. Okay, and again, 2, 4. Let's see. 9, 16, 25, 36, 49, 64, 81, 100. Okay. These, well, actually, it's not even 2. I don't know why I wrote 2. This is 2 squared, 3 squared, 4 squared, and then 5 squared, 6 squared, 7 squared. Okay, these are all the perfect square factors that I'm trying to envision in my actual problem. Okay, and so 4 would be the next number that I would use. So what I would do is I would go to 4, and then if 4 didn't work, I would go to 9, and if 9 didn't work, I'd go to 16, and so on and so forth. Okay, but I know 4 does work. So we've got 4 times 14. Okay, and again, I'm going to underline my perfect square there. Okay, why is it a square? Well, again, because this is an implied 2 right here, right? An implied 2. So I know 4 is a perfect square, so I'm going to just take that 2 out, right? What's the square root of 4? Well, that's 2. And then what remains would be 14. Okay, now I will admit, these kind of problems with variables, I feel like they are a lot more simple than the ones with the numbers. Okay, only because look at the ones with the numbers, you have to actually kind of try to recall perfect square factors. Okay, but I'm pretty sure we get some more. Yeah, we at least get one more. Oh, that's a good one. I like this one. Okay, so we'll go down that list of numbers that I kind of briefly wrote on the previous page. Okay, so we've got the 6 times the square root of 50. Okay, now you probably already have this in your head and you already know, but let's go down this line and let me actually take the time to write out my perfect squares. Okay, so we'll do it right here. So 1 squared is 1. I know it's redundant, but it really helps to know that. So 2 squared So what I'm going to do is I'm going to try to figure out, okay, looking at this 50, which one of these numbers here, right, which one of those numbers will go into 50, okay? Well, 1 obviously does, but we're gonna leave that alone for right now, because 1 times 50. Okay, well, 4 times what will give me 50? Well, let's see, 4 times 12 is 48, and 4 times 13 is 52, so 4 is not going to work. 9, so we got 36, 45, so 9 times 5 is 45, and 9 times 6 is 56, or 54, so that doesn't work. 16 goes to 32, goes to 48, and then that doesn't work, but 5 does, right? Well, 25. 25 times 2 is 50, so we're going to use this 25 here. So what we're going to do is we're going to write this as 6 on the square root of, and then we're going to put 25 times 2, right? 25 times 2 is indeed 50, so again, I'm going to underline that because I'm going to pull it out. All right, so this ends up being 6 times, and then we're going to pull the square root of 25 out, which would be 5, and then leave that square root of 2 in there, and then, well, 6 times 5, that's 30, and we got 30 on the square root of 2. Okay, so that wasn't too terrible. This one looks like a bundle of joy. Okay, so here we go. Simplify the expression. Assume that x, y, and z represent positive real numbers. All right, so nothing new. Okay, so this is a cube root. Okay, so let's go ahead and over here write our perfect cubes. Right. So again, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and then 5 cubed is 125. Okay, so realistically, I mean, for just like super duper quick math, especially for this class, and honestly, college algebra and pre-calc, memorizing your squares like within half a second up to 10, and then your cubes up to 5, you'll be just fine. Okay, so this is a cube root of 40. Okay, so does 40 have a perfect cube factor? Okay, and luckily, yes, right? 8 will go into 40. It will go into 40 5 times. Okay, so we're going to write this as, actually, let's try to keep the same color here that I've been doing. Okay, so 40 is 8 times 5, and again, I'm going to underline the 8 to remind myself that that is the perfect cube I'm going to take out. Okay, x cubed, well, that's awesome, right? X cubed, that is a perfect cube, so I'm going to take that out. All right, so I'm going to have to make this a little bit longer. That's okay, though. Y to the 5th, so times, well, what is the largest multiple of 3 that will go into 5? Well, it's just 3, right? So we're going to say y cubed times y squared, and we're going to underline that y cubed, take it out. And then z to the 7th. Okay, so what is the largest multiple of 3 that will go into 7? Well, that would be 6. Z to the 6th times z. Okay, and then we're going to underline that z to the 6th. Okay, so now we can just start pulling things out, right? So what is the cube root of 8? Well, that's 2, and again, I'm looking at what I'm underlining here. Okay, so what is the cube root of 8? Well, that is 2. Hang on a second. There we go. That is 2. What is the cube root of x cubed? Well, that is x. The cube root of y cubed, that is y. And the cube root of z to the 6th, well, that would be z squared. Okay, and then what remains? Well, that's everything I didn't underline, right? 5y squared z. And I forgot to put my little cube there, so let's erase that so it doesn't get a little messy there. So we're going to say the cube root of y squared z. There we go. All right, so hopefully that wasn't too confusing. I know it's just a little movements kind of suck. Maybe I should write these humongous, right, and then the little movements would just be normal. But that's how we do it. And yeah, we only have two more. Wow, imagine that. All right, so something that many students do, and it's something I run into a lot, and I've run into a lot this semester in my pre-cal course, is many students, and I mean, I'm not calling them out because I did it as well, right? I think it's just a thing that we do. Uh, whenever you learn a new technique, you assume, okay, I'm gonna use that technique, right? That's the first thing I'm gonna do is use that technique. But the thing is, we need to slow down and recall what we've learned before. Okay. So what do I mean by that? Well, let's look at A. Okay, so A, you may be tempted, and let's do the thing where I said I write it big, huh? You may be tempted to write the square root of a to the 7th over the square root of a cubed. Okay, and you can do that, and you will get to the correct solution. You're just adding one or two extra steps. Okay, that's not terrible, right? But if you just recall that when you have a to the 7th divided by a cubed, if you recall, well, that's just 7 minus 3, so it's a to the 4th. Okay, so a is realistically just simply the square root of a to the 4th. Okay, and then, well, that's easy, right? That's just a squared. Okay, so that, and I mean, I won't even say that in my opinion, right? I mean, and in every way you can measure it, that's just quicker than taking the square root of a to the 7th over the square root of a cubed, taking out perfect squares, things like that. It's just easier, right? Same thing with B. Okay, so we've got the cube root of 3 over 81. We could do the cube root of 3 over the cube root of 81, work that out, or we can just go, okay, well, 3 and 81, well, that's just going to be, that's going to end up being the cube root of 1 over 27. Okay, and the cube root of 1 over 27, again, that would now we can kind of break this down. We can say the cube root of 1 over the cube root of 27. Okay, what's the cube root of 1? Well, that's 1. The cube root of 27, that's 3. 1/3. Okay. So for problems that involve fractions, you may, half of you may, again, go in autopilot mode and just go the long way. But if you just slow down on each problem and kind of recall what you've done before, that little time that you take to slow down will actually be quicker for you. And last, but certainly not least, don't you guys love these quick lectures? We cover everything. It's because I don't have to write things on the board. That's what it is. Okay, so let's begin the simplification process. Okay, so we're gonna have 7 on the square root of 50. Okay, well, we've already done a square root of 50, right? We know that we can go and break this down into 25 times 2 over 10. Okay, well, we can take the square root of 25 out, so let's keep consistent and just underline that 25 there. Okay, so we're going to have 7 times 5 on the square root of 2 over 10. Okay, and then, well, 7 times 5, well, that's going to be, let's see, can we, 35. Yeah, we'll do it that way. There's a couple ways we can go about it. We're going to do it this way, though. So we're going to go, okay, well, 7 times 5 is 35 on the square root of 2 over 10. Okay. And then what we're going to do next is we're going to reduce this, okay? So 35 and 10, right? 5 will go into both of them. 5 will go into 10 2 times, and 5 will go into 35 7 times. Okay? So this becomes 7 on the square root of 2 over 2. Okay, and I guess that's it. So before I do say, that's the end of the lecture, uh, the only thing that we really introduced today well, I mean, I guess would be the actual the topic, right? But once you take out your perfect square, your perfect cube, whatever, then just becomes this arithmetic that we've been doing all semester long, right? Anyways, that does conclude today's lecture.